Welcome to Scholars Air Tutorial. In this video, we'll be looking at dimensional homogeneity. In our last video, we talked about dimensional analysis, so this will be our last video on anything concerning dimensioning. Our first video was dimensioning. If you've not watched it, go and watch it. I'll drop a link. I'll leave a link to dimensioning, and also I'll leave a link to the last video, which was dimensional analysis. So this video will be looking at dimensional homogeneity. Now, when we say something is homogeneous, what do we mean? We actually mean that that thing is the same. The stuff is the same. So when we talk about dimensional homogeneity, we are just saying having the same dimension. Now, the principle of dimensional homogeneity states that in any correct physical equation, all dimensions must be the same. Meaning that if you're adding, if you're subtracting, or carrying out any operation on physical quantities, they must be made of the same dimension. That is just what we are trying to say when we talk about dimensional homogeneity. So let's try out something. First of all, let's illustrate this whole explanation and concept with maybe an equation. Okay, let's look at one of the equations of motion. So our work now is to determine if this equation is dimensional homogeneous. This whole equation, if it's dimensional homogeneous, that is our primary duty. Now, so first thing, you list out everything given here. Each of these quantities is given here, so we list them out, and we'll also write out their dimensions. List them out and write out their dimensions. So these are the dimensions for these quantities. Now, if you don't have got this dimension, you can check our last video, one of the previous video, where we talked on dimension, how to dimension physical quantities. So this is distance. S here represents distance, which is this, and the dimension for distance is L. U represent initial velocity, and the dimension for initial velocity is L per t. T here represents time, the dimension for time is t, and A here represents acceleration. Dimension for acceleration is L per t square, and this t also represents time. So now, when checking for dimensional homogeneity, we don't include the coefficients. So this coefficient is not really the main focus. What we are focusing on is the quantities given and not really the coefficient. So what are we going to do now? We are going to rewrite this equation in form of, or in terms of, these given dimensions. Writing these equations in terms of these given dimensions. So if we do that, we have L here represents the distance, which is S. So we have L per t here represents U here, which is the initial velocity. So we have them dot here means represents multiplication. So you can see UT. So L per t dot t, this t here represents time. So UT, which is U multiply t, is also same thing as L per t multiply t. Then we have the plus here, and we have 1/2 here. Then acceleration, which is A here, we use L per t square, then dot t square. You can see that our t here has square, so we add the square. Next thing is we express these terms. So looking at this, let's solve for this side first. This is the UT terms. Let's solve for it. Then we solve for AT square terms, and we'll see what we can do from there. So looking at this, we recall in indices, when you have two bases, you pick out one. So we have t here, What do? We pick out one. Now -1, and when you pick out one, what do? You add their powers. -1, and what is power of t here? 1. So -1 plus 1 give us what? 0. So we have LT to the power of 0, Next thing here, plus half. We bring down this half. We have two bases here that are the same, t and t, and we add their powers. Negative 2 plus 2 give us what? 0. So we have lt to the power of 0. Solving this, we have L equals lt to the power of 0 plus 1 over 2 lt to the power of 0. Now, recall that anything raised to the power of 0 equals 1. So t to the power of 0 means 1 and t to the power of 0 means 1. So we'll be having L into L bracket 1 plus 1 over 2 L bracket 1. Now L times 1 is what? L. L times 1, L. So we'll be having L equals L plus 1 over 2 L. So with this, we can say that this equation, these quantities, they are dimensional homogeneous. This equation follows the principle of dimensional homogeneity because all the terms here are L. You can see L here, L here, and L here. Now recall I said not minding the coefficient. Not mind the coefficient. So we have L here, L here, and L here, meaning that they are dimensional homogeneous. So it's that easy. Now we can say that this equation, they are dimensional homogeneous. Let's look at second example. So our second equation here, v squared equals u squared plus 2as. We are asked to find if this equation is correct. Same thing as saying if this equation is dimensional homogeneous. So like I said, the first thing you have to do is to write out each of these quantities given and their dimensions. So for our v, we have velocity, which is L per t. Our u, we have initial velocity, which is L per t. This vr represents final velocity. So this a, we have a, which is acceleration, L per t square, and we have s, which is displacement, as L. Next thing is to rewrite this equation in terms of these dimensions. So where we have v, we will substitute for L per t. Where we have v, we substitute for L per t. Where we have a, L per t square. Where we have s, L. So we have L per t all raised to the power of 2. Remember, our v here has square, so L per t to the power of 2, and same for u, L per t to the power of t plus 2as. So this is our a and this is our s. Now when we have something in bracket like this to the power of 2, it means that these two will multiply everything in this bracket. So these two will multiply everything in this bracket. So we are going to express these quantities here in terms of their square. So we'll be having L square multiply t raised to the power of negative. This negative 1 now, we multiply this 2. So negative 1 times 2 gives us what? Negative 2. So we're having t to the power of negative 2. Same thing will happen here. And then we will rewrite this because we don't have any power outside the bracket. So now we have L square per t square equals L square per t square plus 2L per t square multiply L. Now you can see that these two now are the same. The only problem now we have is this one. So recall that I said when you have two bases multiplying that are the same, you pick out one and add their powers. So what is the power of L here? 1. What is the power of L here? 1. So 1 plus 1 will give us what? 2. So we are now having L square. So we have L square per t square equals L square per t square plus 2L square per t square. Remember, I said not minding the coefficient. So this coefficient somehow is insignificant when we are checking for dimensional homogeneity. So we can see that this equation is dimensional homogeneous. This equation is dimensional homogeneous, and we can see that this equation is correct. Now this dimensional homogeneity is used to check if equations are correct. Remember I said that the principle of dimensional homogeneity states that in any correct physical quantity, all dimensions must be the same. Whether you're adding or subtracting or carrying out any operation on physical quantities, they must be the same. They must be of the same dimension. So you can see that here we have for v square, this is dimension. This is the same as that for u square and same as that for as, which is this. So you can see that this equation is very correct. So this is all on dimensional homogeneity, and I guess you've learned something from this video. So please subscribe, like and comment. And what if you don't know how we got these dimensions, watch out for our previous videos on dimensioning and dimensional analysis. Subscribe, like and comment.